Welcome back. We will again now continue discussion on the Dirichlet problem which started in the previous lecture. Let me again just okay. So, this is the Dirichlet problem we are trying to find the solution. So, we have to find the value u b and u c. u d is provided by the boundary conditions. So, we have so let me write the coordinates of the point D B C. So, D is nothing but, so it is on the boundary line. So, that is x equal to 0 and its t variable is x by c. So, here the characteristics are straight lines. So, you have to just compute the intersection of two lines. So, it is little bit of work, but you do it. Okay. So, that is no problem there, and no, this is not okay. Let me just change some notation here. Okay, that is D. D is that is fine. So, then B so this is the intersection of the characteristic passing through the point x 0 and the characteristics passing through the point x t. So, this is you have to do some algebra here. I am skipping that algebra. Plus x minus plus x 0. One by 2 c c t plus x minus x 0. So, you have to remember this, you have to remember x is less than c t. We are in that region. Okay. So, this t minus x by c is positive. So, it is in the positive t axis, and the point C is half c t minus x plus x 0 to c c t minus x minus x 0. We want both this B and C in the region, in the first quadrant of the region. So, the x coordinate and t coordinates obviously are positive. Okay. So, for this region, so this in order that this is positive. Okay. So, we assume, so this is the smallness x 0 is at our disposal, x 0 is less than c t minus x, and c t minus x is positive. So, I can always find an x 0 satisfying that condition. So, there is no problem finding x 0, and soon we will see that x 0 does not appear in the final formula for the solution. So, it is just like a catalyst. So, now u of d is simply h of t minus x by c. D is the point on the boundary line. So, there is no problem at all. Okay. And now again I want you to do some simple computation. So, by D'Alembert's formula, so you see how the D'Alembert's formula is repeatedly used. We have u of u of b and u of c. U of b is half u 0 c t plus x plus u 0 c x 0. Just you find the domain of dependence of this point B and just apply the D'Alembert's formula. That is what I am doing. u1 y t y, some dummy variable of integration, and similarly u of c is half u 0 c t minus x plus u 0 x 0 x 0 dy. So, we have found the solution at all these 3 points. So, at u of d it is provided by the boundary condition, and at b and c it is D'Alembert's formula that provides the solution. And now again you go back to CPP. Okay. So, u of a is given by this. So, just plug in there, that is all. So, CPP, let me recall that, implies u of x t, u of x t we have denoted by the point A, and this is just u of d, let me write that, u of b minus u of c. Okay. So, we have the expressions for all these things. So, let us put them together. So, therefore, u of x t, u of d, which is nothing but t minus x by c, u of b plus u of b. So, let us again recall that u of b is here, half u 0 c t plus x plus u 0 x 0 plus 1 by 2 c x 0 to c t plus x u 1 y dy. So, this term will be u of b minus half u 0 c t minus x plus u 0 x 0 minus 1 by 2 c x 0 to c t minus x u 1 y dy. So, let us simplify that. Okay. So, that u 0 half u 0 x 0, there is minus half 0 u 0 x 0. So, that just so x 0 you can choose any arbitrary point. So, it does not influence the solution at all. So, this h of t minus x by c plus half u 0 c t plus x. Now, there is a minus here. So, u 0 c t minus x. And now, we can combine these two integrals. So, this is the integral from x 0 to c t minus x, this is from x 0 to c t plus x. So, you can write this integral as x 0 to c t minus x and then c t minus x to c t plus x, and one term cancels with this. So, we have just 1 by 2 c c t minus x c t plus x u 1 y dy. Okay. So, again remember, let me stress that. So, x is, this is in the region above the characteristic x equal to c t. So, it is x less than c t. So, let us combine both the formulas. So, let us write in single formula. So, therefore, we have u x t depending on the position of the point. So, in x bigger than c t, it is given by the D'Alembert's formula. So, let me write that. This is for x bigger than c t. Okay. So, when x is less than c t, we obtain this one. So, there is boundary thing coming. So, let me write that separately, plus half u 0 C t plus x minus C t minus x, that is plus 1 by 2 c. So, the expression for the solution is given separately for the regions x bigger than C t and x less than C t. So, what about x equal to C t? So, that part still missing, and before that, so we understand what is this x minus C t and x plus C t, but what is this C t minus x? So, let me just geometrically show where does that lie. So, this when x is less than C t. So, again just x equal to C t. So, here is the point x t. So, there is a characteristic meeting the boundary line x equal to 0, and then you draw the, so it is kind of reflected characteristics, and this is the point C t minus x 0, and that is the reason it also appears with a negative sign here. So, watch that one. Okay. So, what about this solution on the solution on x equal to C t? Okay. So, we can simply take limit of the solution. So, we have found the solution in this region and this region. So, we simply take limit from either side. So, obviously, we want solution to be C 2, and that imposes certain conditions on the boundary data and the initial conditions. Okay. So, two expressions are here. So, for example, let us compute the limit u x t as x approaches C t, or in fact, you can even do better. You can take y s y s approaches C t t, t is any positive number, the only condition is that so we are taking limit when y is bigger than C t C s and y less than C s. So, you have to take two limits now. Okay. So, you get when y is bigger than C s, we are in this region. So, when you take approach y s to C t t, so this goes away, x is C t. So, what you get is half u0 2ct plus u0 0 plus 1 by 2c 0 to 2ct u1 y dy. So, if I use the first expression, that is what the limit I get, and if I use the second expression, that is valid for y less than Cs, that one. So, again I get half u0 2ct, you have to do it carefully, minus u0 0 plus 1 by 2c 0 to 2ct u1y dy, and there is of course boundary term. So, that is coming h0. So, I calculate this limit of the solution when the point approaches this line from above and from below. So, I get two expressions. So, in order that u is continuous, so these should be equal, and that gives us one condition. So, for u to be continuous, across the line, characteristics x equal to c t, we require the condition h0 equal to u0 0. Okay. So, similarly, you can work out the conditions for the solution to be C1 and C2. Okay. So, similarly, similar limits can be obtained for u to be a C2 function. See, this is the minimum thing we require. C2 function. So, let me write down. So, it is a bit computation. So, you can, so similarly you can differentiate this expression with respect to either x or with respect to t, and similarly uxx, uxt, everything. So, you will get two more conditions. Okay. So, we obtain, so this is bit work. Okay. So, we have to do some computation. So, let me write that first condition h0 is equal to u0 0, then h prime 0, just check whether u1 0 and h double prime 0 is c square u 0 double prime 0. Okay, just check the okay, I just. So, these are called compatibility conditions. So, these are required for the smoothness of the solution. These are called compatibility conditions. Compatibility conditions. So, that are required to satisfy between the boundary data and the initial conditions. So, this H is boundary condition and u 0 u 1 are the maybe there is a C missing here, just check that. Okay. Compatibility conditions. So, thus if H u 0 are C 2 functions and u 1 is a C 1 function in their respective domains, and the compatibility conditions are satisfied, compatibility conditions are satisfied, then the solution u is a C 2. In the first quadrant, that is important. And we have obtained a formula for that. So, in case any of the here there are three conditions, any of the compatibility condition is not satisfied, then you will suffer that corresponding discontinuity either in the function itself or in the derivative across this characteristic. Again, just recall, so any discontinuity in the initial condition we saw that propagates along the characteristics, and similarly here if the compatibility condition is not satisfied, any of them, then the solution will suffer that kind of discontinuity across that single characteristic, namely x equal to C t. So, this completes the solution of the Dirichlet problem. Okay. So, let me just mention, so another kind of Neumann condition, Neumann boundary condition, or even mixed conditions. So, Neumann condition, instead of u, you provide the data for the first derivative with respect to x, and that is in this case it is the normal derivative of u, normal to the that line, it is in the x direction. So, you are providing the first derivative, and this is more difficult than the Dirichlet one, we will see that. And more generally we can also give mixed boundary condition, more generally mixed boundary condition. Alpha u 0 t plus beta u x 0 t equal to h t. So, these may be different functions, I am just writing general things. So, these are given functions. So, if alpha equal to 0 we get, and beta is not equal to 0, we get Neumann boundary condition, and beta equal to 0 and alpha not 0 we get Dirichlet boundary condition, that we already seen it. And if both are non-zero, then this is a mixed problem, we will see that. Just one remark, just we will come to an end of this lecture. In the Dirichlet boundary value problem, suppose the boundary data, suppose h is identically 0. So, just let me show you that. So, I am taking this h identically 0. In that case, there is a simple way of obtaining the formula by converting the problem into the entire line problem. Okay. In this case, so this is 0. Solution formula, solution may be obtained easily. How you are doing that thing? So, extend u0 u1. So, u0 and u1 they are defined only for x positive. So, you extend to r as odd functions. Odd functions, and use this extended functions as the initial value for the wave equation in the entire domain, and then you apply the D'Alembert's formula, and then you will get this. Yeah, this when h equal to 0, you precisely get just by solving the wave equation in the entire real line, h equal to 0. So, this you cannot do when h is not 0. So, with that thing we will come to end of this class, and in the next class we briefly study the Neumann boundary condition and see how the formula changes, and that little more work, but we will do that so that you will get an idea how the formula changes. Thank you.